Good morning, everyone. I am Usman K, Assistant Professor, BITM Ballari. First, I welcome you all to my fourth video lecture on Module 3. So, in the previous class, we discussed about three-dimensional geometric transformations. So, we learned how we can perform various types of operations on a given object. So after completion of three-dimensional geometric transformation concept, today I would like to introduce clipping algorithms. So first we will learn what is clipping and what are the various types of clipping algorithms computer graphics will support. Next, we will solve few problems on a clipping algorithm. After that, we will implement one of the line clipping algorithm. So, what is clipping means? In computer graphics, whenever we want to display any object on the screen of the monitor, first we need to check whether that object lies inside the clipping window or outside of the clipping window. So, whichever the part of the object that lies outside the clipping window, we need to clip that part of the object, and whichever the part of the object that lies inside the clipping window, we need to display that part of the object on the screen of the monitor. So this is the objective of clipping algorithms. So the definition of clipping is very simple. It is a process of determining which part of the object that lies outside of the clipping window. So whichever the part of the object that lies outside the clipping window, we need to reject those pixels, and whichever the pixels that lies inside the clipping window, only those pixel informations we need to accept, and we need to display those pixels information on the screen of the monitor. So in computer graphics, we are using various types of clipping algorithms. Like we have point clipping algorithm, next line clipping algorithm, third one is fill area clipping algorithm, fourth is curve clipping algorithm, fifth one is text clipping algorithms. So these are the various types of clipping algorithm we are using in computer graphics. But in module 1 and 2, we learned only three geometrical primitives, like how to create a point or how to create points in a OpenGL. We learned this. Second geometrical primitive, we learned how to create a line segment. And third geometrical primitive is called polygons. So we learned how to create a polygon. Now we would like to apply clipping algorithm only on these three geometrical primitives, like points, like lines, like polygons. But curve clipping and text clipping, it is not there for our syllabus. So let's begin how to perform clipping on point, on line segment, on a given polygon. So first type of clipping is called point clipping. Means we need to determine whether point lies inside the clipping window or outside of the clipping window. If point is lies inside the clipping window, we need to accept that point and we need to display on the screen of the monitor. In case if that point is lies outside the clipping window, then we need to reject that particular pixel position in a two-dimensional plane. So whenever we are performing clipping, we need to specify our clipping region, or we need to specify which position of the two-dimensional plane is required to display the image on the screen of the monitor. So as I displayed two columns, two columns. In the first column, we are using two-dimensional viewing. In the second column, we are using three-dimensional viewing. Means whenever we want to use clipping concept in our OpenGL program, we need to define one rectangular window. That rectangular window or a square window represent it is a clipping window. Means any part of the object, if it is within the clipping window, only that part of the object is visible or it is displayed on the screen of the monitor. So what I would like to say here means, if I want to implement clipping concepts in our OpenGL program, we have two types of windows. If we are using two-dimensional viewing, our clipping window is either it can be rectangular shape or it can be square shape, because in two-dimensional we have only x coordinate and y coordinate. So I specified what is the standard position of the our clipping window. So the standard position of the clipping window in case of two-dimensional plane is, as you can see, that bottom left corner I written x min y min. This is the position of the clipping window in our OpenGL program. So x min y min, and I written one more position of the clipping window x max y max. Means our clipping window ranges from x minimum to x maximum with respect to x axis, and y minimum to y maximum with respect to y axis. So this is the size of the clipping window we defined in a two-dimensional plane, or in case of two-dimensional Cartesian reference frame. So how to apply this clipping concept with respect to point in a two-dimensional plane means, if you take any point, assume that I have taken one point P and its coordinate position, assume that x and y, x and y. If this point P position is x and y, I need to check that whether it lies inside the clipping window or outside the clipping window. So how to determine whether it lies inside the clipping window or outside the clipping window means, we need to check this range. If a given point x coordinate value, I written x, please you see the mouse pointer. If x coordinate value of the point is within the range of x min to x max, that is x value should be greater than or equal to x minimum, and it should be less than or equal to x max, then you can say that given point P, its x coordinate ranges within the clipping window. And you also check that whether y coordinate ranges from y minimum to y maximum or not. So if y coordinate value, if it is greater than or equal to y minimum, and if it is less than or equal to y maximum, it means that for a given point P, its y coordinate is also lies inside the clipping window. Then we need to accept this point P and we need to display this point P on the screen of the monitor. So when point P lies inside the clipping window, no need to perform any clipping on this particular point P because it lies inside the clipping window. In case if this point P lies outside of the clipping window, then you can say that we need clipping algorithm here to clip that particular point that lies outside of the clipping window. This is about two-dimensional plane. Assume that if we are using three-dimensional plane, means we are using three-dimensional Cartesian reference frame, then we need viewing volume, means our clipping window is not like a rectangle or it is not like a square. It looks like a cube because we want to clip a given three-dimensional object. When you want to clip given three-dimensional object, then you need 6 different viewing planes. So how to generate 6 different viewing plane means this cube generate 6 different viewing plane, 6 different two-dimensional viewing plane. As you can see that, so in the front end we have one viewing plane or clipping window, and we have top end is also one of the clipping window, and either sides we have totally 4 clipping window. Means the shape of the viewing volume in case of three-dimensional Cartesian reference frame is nothing but one cube structure. So if you want to check whether point P in a three-dimensional viewing, whether it lies inside the clipping window or outside the clipping window, how to determine means take a point P of coordinate position I written clearly here x, y, z. Check that whether this x, y, z ranges within the range of x minimum to x max, y minimum to y max, and z minimum to z max. If given point P is lies within this range, then you can say that given point P lies inside the viewing volume. So whichever the object or whichever the point that lies inside the viewing volume or inside the cube, we can display that point on the screen of the monitor. If any point that lies outside of this cube, then we cannot able to display that point on the screen of the monitor. So in this slide I am explaining what is the shape of the clipping window either in two-dimensional plane or in three-dimensional plane. In case of two-dimensional plane, our clipping window looks like a either rectangle or it looks like a square, as you can see in the slide. But in case of three-dimensional plane, our clipping window, we should not call it as a clipping window, we should call it as a clipping volume. So the shape of the clipping volume is like a cube. So here I explained how to perform point clipping. So let's move to next topic, that is how we can perform clipping on a given line segment. So here we are discussing only how to perform clipping on a straight line. How to perform clipping on a straight line. So in computer graphics, there are various types of line clipping algorithms we have. But here we are discussing Cohen-Sutherland line clipping algorithm. So the working principle of Cohen-Sutherland line clipping algorithm is simple. But before going the working principle of Cohen-Sutherland line clipping algorithm, as you can see this slide, we are discussing all the algorithms only with respect to two-dimensional Cartesian reference frame. Now, as you can see that I defined one clipping window. The red color represent it is nothing but one clipping window. Now I would like to perform line clipping with respect to this particular diagram. So as you can see that whenever I want to define a line segment, we know that we need to define two endpoints of the line segment. So as you can see that I defined 5 line segments, 1, 2, 3, 4, 5 line segments. So when I want to apply line clipping concept in a given line segment, now I need to perform line clipping algorithm like this. Assume that I would like to apply Cohen-Sutherland line clipping algorithm on a given line P1, P2. So as you can see that both the endpoints of the line segment, I am discussing about first line segment called P1 to P2. When both the endpoints of the line segment lies outside the clipping window, then we need to clip this line segment. Means we need to reject this particular line segment. So no need to display this line segment on the screen of the monitor. So this is a one case. And here also one more line is there, P9 to P10. So no need to display this line segment on the screen of the monitor because both the endpoints of the line segment lies outside the clipping window. This is the first case. Means we have 4 cases here. Second, you can see that third line here. If you take a line segment P3 to P4, both the endpoints of the line segment lies inside the clipping window. When both the endpoints of the line segment lies inside the clipping window, then we need to accept this line segment and we need to display this line segment on the screen of the monitor. This is second case. Third case, you can see here, that is line number P5 to P6. I am telling endpoints of the line segment. So if you see line P5 to P6, one endpoint of the line segment lies outside the clipping window and one more endpoint of the line segment lies inside the clipping window. So when one endpoint is inside and one more endpoint of the line segment is outside, then we need to determine intersection point here. So what is the intersection point means? The intersection point is nothing but it is a intersection between boundary edge of the clipping window and our line segment. So we will get one intersection point between P5 to P6. That is nothing but I can say that P5 dash P5 dash. So from the P5 dash to P6, we need to generate one particular line segment. We need to generate or we need to draw one line segment with respect to this particular example like this. So these are the various types of cases we are discussing here. Various types of algorithm. These are the various. So in this method, we have four cases are there. 4 cases are there to perform clipping. So case 1 is two endpoints of the line segment that lies outside the clipping window. This is the first case and we discussed. Second case is called two endpoints of the line segment. It lies completely inside the clipping window. When two endpoints of the line segment lies inside the clipping window, we need to accept that line segment and we need to display that line segment on the screen of the monitor. This is the second case. Third case I said one endpoint of the line segment that lies outside the clipping window and one more endpoint of the line segment that lies inside the clipping window. Then we need to determine intersection point between P5 to P6, and from that intersection point to the endpoint that lies inside the clipping window, we need to display only that part of the line segment on the screen of the monitor. This is the third case. Fourth case is two endpoint of the line segment that lies outside the clipping window, but part of the line segment that lies inside the clipping window. So in this situation, we need to determine two intersection points. As you can see the diagram, line from P7 to P8. Here, I need to determine two intersection point. Then I need to plot the line segment on the screen of the monitor. So as you can see this is the image before performing clipping. So after performing clipping, you see the output. You see the output. The two line segments that lies outside the clipping window, it is completely rejected. Means it is discarded or it is clipped out. And whichever the part of the object that lies inside the clipping window, we displayed only that part of the line segment on the screen of the monitor. So this is the objective of Cohen-Sutherland line clipping algorithm. So let's begin with working principle of Cohen-Sutherland line clipping algorithms. So if we want to perform line clipping algorithm, if I want to perform line clipping, then first we need to divide given two-dimensional viewing plane or view plane into 9 regions. As you can see that this is the diagram. Assume that this is the region where we want to display the image on the screen. So what we did means we divided this two-dimensional viewing plane into 9 regions. So as you can see that this is the one region. Region means area. This is the one area. Second, third, fourth, fifth, sixth, and 7, and 8, and 9. So this view plane is divided into 9 various types of regions. Now, in which region we can able to view the object means, if any object that lies in the region called phi, as per my example I am telling, if any object that lies in the region called phi, only that object, that part of the object is accepted and it is displayed on the screen of the monitor. If any part of the object that lies other than the region area called phi, means either it can be lies at the area called 1 or 2 or 3, 4, 6, 7, 8, 9, then we need to perform clipping that part of the object. So this is the one of the requirement of Cohen-Sutherland line clipping algorithm. So as I said in the previous slide, we have various types of line clipping algorithms are there. Among those various types, Cohen-Sutherland line clipping algorithm, it is one of the fastest line clipping algorithm. It is one of the fastest line clipping algorithm. So this is one of the advantage of Cohen-Sutherland line clipping algorithm. So the basic requirement I said in case of Cohen-Sutherland line clipping algorithm. So let's begin with what are the steps we have in case of Cohen-Sutherland line clipping algorithm. So we'll go step by step. You will get the clarity how we can clip given line segment. So if we want to use Cohen-Sutherland line clipping algorithm, we first, as I said in the previous slide, first we need to divide given two-dimensional view plane into 9 regions, and we need to assign a region code or out code to each region among the 9 regions in a two-dimensional view plane. And we also we need to enter two endpoint of the line segment. So as I will assume here, my first endpoint of the line segment is P1 and its position is x1 y1, and P2 is the second endpoint and its position is x2 y2. So in the first step, what we need to do means we need to assign unique out code to each region of the two-dimensional weaving plane, and we need to enter two endpoint of the line segment. This is the first step. Then we know the two endpoints of the line segment. Then the question is, what is the meaning of out code, or how to prepare region code for each region of the two-dimensional plane. So what is out code means? Out code is a 4-digit binary number. It represent, or each bit position in out code represents position of the endpoint. Means each bit position in a 4-digit binary number, it represent, or it tells that whether that endpoint lies inside the clipping window or outside of the clipping window. So with the help of this out code, I can decide whether endpoint of the line segment lies inside the clipping window or outside the clipping window. So as you can see that how we can prepare 4-digit out code. So as you can see that in this slide, whenever you want to assign unique out code to each region of the two-dimensional plane, you need to remember this formula, that is top, bottom, right, left. Top, bottom, right, left means how many bits are there means here 4 bits are there. I said out code can be represented using 4 bits. 4 bits. So first bit position represent top, second bit position represent bottom, third bit represent right, fourth bit represent left. These are the 4-bit out code we are using to assign the out code for the each area of the two-dimensional plane. So as I written TBRL, so this is nothing but 4-bit position. So totally 9 regions are there, I said. So as you can see that, so we have 4-bit number. For example, I am taking one example. Assume that I want to assign unique out code. Please you see the mouse pointer. I want to assign unique out code to this region. So how to assign unique out code to this region means we are using 4-bit number here. So in this 4-bit number, I will read from left to right. First bit position represent top area or top region of this two-dimensional plane. If this first bit is 1, it means that it is a top area from the coordinate position x minimum to x maximum. So this is the first bit position, and remaining all 3 bits are 0. This is the top area. As you can see the bottom area. In the bottom area, second bit position is I substituted 1. Means here top, bottom, right, left. Now bottom value I substituted 1 and remaining all the bits are 0. If 0, 1, 00 is there, it means that it represents that given point lies within this area, and this area code is 0100, and the range of this code is x minimum to x maximum. I am reading here x minimum to x maximum. This is bottom. Similarly, if third bit is 1 in a given out code, if third bit is 1 and all the bits are 0, all the other bits are 0, it means that this is the region code for this particular area. So this region code ranges from y minimum to y maximum and only within this area. Similarly, if fourth bit is 1, if fourth bit is 1, it indicates this is the out code or region code for this particular area, and its code ranges from y minimum to y maximum. If all the bits are 0, means if the out code all the bits are 0, it means that that particular point lies inside the clipping window. So what I said in the previous slide, I given name for 5 for this area. Now as per the algorithm, the region code for inside the clipping window is all the bits are zeros. If all the bits are zeros, means if the outcode values are all the bits are 0, it means that that given point P, for example the given endpoint P, if it is lies in this area, it means that we need to accept that endpoint. If that endpoint lies other than this area, other than this area means totally we have 9 regions, totally we have 8 regions. If that endpoint lies among the 8 regions other than 4 zeros, it means that we need to perform clipping. So as we learned here how to assign region code for the top, bottom, right and left and center here, but how to get 1001, 1010, 0101, 0110? If you want to assign, if you want to generate this outcode, please you see the mouse pointer. If you want to generate the outcode or region code for this area, we need to perform bitwise OR operation between the outcode top and left. If you perform bitwise AND operation between top and left outcode, you will get the outcode for this area. So we know that the working principle of bitwise OR operation. So in case of bitwise OR operation, when we are applying bitwise OR operation between top and left outcode, when both the bits are 0, then only output is 0. If any one of the bit is 1, if any one of the bit is 1, then output is 1 only. So based on this principle, I would like to perform bitwise OR operation between this top outcode and left outcode. So assume that I return top outcode 1000, left outcode I return below this 0001. So if you perform bitwise OR operation, I will perform bitwise OR operation 1 bitwise OR operation 0, 1 OR 0, output is 1, I return 1 here. Similarly 0 bitwise OR, outcome is 0, 0 bitwise OR, outcome is 0, 0 bitwise OR, outcome is 1. Means with the help of outcode top and left, I generated outcode for this particular area. Similarly, you need to perform bitwise OR operation between top outcode and right outcode. If you perform bitwise OR operation between top outcode and right outcode, you will get 1010. Similarly, if you perform bitwise OR operation between bottom outcode and right outcode, you will get 0110. Similarly, if you perform bitwise OR operation between left outcode and bottom outcode, you will get 0101. So as per the step 1, we assigned outcode to each region of the two-dimensional plane. Now we need to determine whether those endpoints of the line segment lies inside the clipping window or outside the clipping window. So inside the clipping window means output should be all the 4 bits are 0. Outside the clipping window means if any one of the bit or if any 2 bits in a given output is 1 means it lies outside the clipping window. What I want to say means if output of the endpoint is other than 4 zeros, definitely that endpoint lies outside the clipping window and we need to perform clipping that particular endpoint. So this is the step 1. Now we'll move to step 2. But before going to step 2, we are using few equations here. We are using equations here when we need to accept the line segment and when we need to accept, when we need to reject the line segment. So that is called equations here or conditions here, right? Assume that I defined two-dimensional clipping window here. So inside the clipping window, we know that output is all the 4 bits are 0. Assume that I have taken one point P here. I have taken one point P. I want to determine whether this endpoint lies inside the clipping window or outside the clipping window. So how to define whether it is inside or outside means we have various conditions here. So if I want to specify given point P, x and y coordinate lies inside the clipping window, when I can say that the given point P lies inside the clipping window means if your x coordinate value of a given point, if it is greater than or equal to x minimum and less than or equal to x maximum, I can say that x coordinate value of a given point P lies inside the clipping window and y coordinate value should be greater than or equal to y minimum and less than or equal to y maximum. Then I can say that given point P, y coordinate value lies within the clipping window. When both the coordinate value x and y coordinate value lies inside the clipping window, then we need to accept that endpoint. Accept that endpoint means it lies inside the clipping window. So as per the program, we are assuming it is 0. If it is 0, we need to accept. In case if this x value is less than x minimum, then we need to reject that particular point. If x value of that particular point is less than x minimum, it is out of range. Means that point coordinate position is not inside the clipping window. So we need to reject. If x coordinate value, if it is greater than x maximum also, then also we need to reject that point. Then rejection can be represented 1 in our algorithm or in our program, right? Reject is represented by using 1. Accept is represented by 0 here, right? This is with respect to x coordinate. Same as with respect to y coordinate. So when we need to reject means if given endpoint y coordinate position is less than y minimum, then also we need to reject. If y axis value, y coordinate position, if it is greater than y maximum, then also we need to reject. So these are the 4 conditions are there. So we'll get the 4 bits. So I can say that first bit is y is greater than y max. Second bit is y is less than y min. Third bit is x is greater than x max. Fourth bit is x is less than x min. So when we are solving problem, we need these 4 bits: 1, 2, 3, 4. So based on these 4 bits only, we need to decide whether we need to accept that endpoint or we need to reject that endpoint like this. So these are the 2 equations we are using in Cohen-Sutherland line clipping algorithm. So I completed only step 1. So step 2 says that we need to determine output of the given line segment. So as we know that in the step 1 we entered 2 endpoint of the line segment. Assume that we entered P1 and P2. So here I did not return P1, P2 here. Here we need to determine what is the region code for the endpoint P1 and P2. So I am assigning O1 represent output of first point P1 and O2 represent output of the second point P2. So here we are assuming O1 and O2 are the outputs of the given line segment. So in the step 2 we have four cases. In step 2 we have four cases. So we'll discuss one by one. So assume that in case 1 assume that in step 1 we entered two end point of the line segment, that is P1 and P2. In step 2 we determined what is the output of the P1. So assume that output of the P1 is O1 and output of the endpoint P2 is O2. After calculating O1, output 1 and output 2, if first case, if output 1 and output 2, if both are is equal to 0, it means that both the endpoints of the given line segment completely lies inside the clipping window. When both the endpoints of the line segment outputs are 0, it means that it lies inside the clipping window. Then the entire line is accepted and we need to save that, and we need to display that line segment on the screen of the monitor. So as you can see this example, we have 5 lines here, 1 2 3 4 5. So with respect to this 5 line segment, with respect to case 1, I can say that a line segment P3 P4, assume that P3 output is O1, P4 output is O2. So output of the P1 is also 0, output of the P2 is also 0. It means both the endpoints of the line segment lies inside the clipping window. Then we don't want any clipping concept here. We need to accept. This is case 1. We'll move to case 2. But before moving to case 2, I want to make case 1 is false. Means assume that output O1 and O2, it is not equal to 0. If output O1 and O2, if it is not equal to 0, then we will move to case 2. So in the case 2 I written else if, means first condition is false. If first condition is false, then as you can see that if outputs O1 and O2 here, if it is not equal to 0, then what we need to do means, in Cohen-Sutherland line clipping algorithm, we need to apply bitwise AND operation between the output O1 and O2. So if you apply bitwise AND operation between O1 and O2, assume that the result of the bitwise AND operation is not equal to 0. If the result of the bitwise AND operation is not equal to 0, what it means then both the endpoints are outside the clipping window. Means both the endpoints are lies outside the clipping window. Then we need to reject this particular line segment. Or we need to discard this line segment. Why means, after applying bitwise AND operation between the two outputs, we are getting result, it is not equal to 0. If it is not equal to 0, it means that both the endpoints are lies outside the clipping window. So as you can see this example, here 5 line segments are there. With respect to case 2, you can see that a line segment P1 to P2. So if you calculate output 1 and output 2 for the P1 and P2, output 1 and output 2 is not equal to 0. If it is not equal to 0, then we want to apply bitwise AND operation. After applying bitwise AND operation, you will get a non-zero result. If you are getting non-zero result, means both the endpoints lies outside the clipping window. So here two examples are there. We need to reject. P1, P2 is also we need to reject, and I think P9 and P10 it is not visible, but P9 and P10 is also we need to reject. This is the two line segment with respect to case 2. Assume that this case is also false. This case is also false. This case is also false means after performing bitwise AND operation between output 1 and output 2 between two endpoints, result is not equal to 0. If result is not equal to 0, then we'll move to case 3. So in the case 3, as you can see that here in the case 3, after applying output after applying bitwise AND operation between output O1 and O2, assume that result is equal to 0. If result of the bitwise AND operation is equal to 0, it means that no doubt that both the endpoints of the line segment lies outside of the clipping window, but part of the line segment lies inside the clipping window. Then we need to determine intersection points recursively in which line crosses the window. Means here we are using recursion concept here to determine the intersection point. So with respect to case 3, with respect to this example, which line indicates two endpoints are outside the clipping window, but part of the line segment is inside the clipping window. Means as you can see that P7 to P8, P7 to P8, this is the example where two endpoints of the line segment lies outside the clipping window, but part of the line segment lies inside the clipping window. Then we need to determine two intersection point. First intersection point is called P7 dash, and one more intersection point is called P8 dash. So after calculating two intersection point recursively, that is P7 dash and P8 dash, we need to clip the part of the object that lies outside of the clipping window, and whichever the part of the object that lies between two intersection point, we need to accept, and we need to display that part of the line segment on the screen of the monitor. So assume that case 3 is also false, means case 1 is also false, case 2 is also false, and case 3 is also false. If case 3 is also false, definitely case 4 has to become true. So what is the case 4 means? So assume that case before going to case 3, I would like to discuss how to determine intersection points. Means what are the formulas we are using to determine the intersection points, because in case 3 we need to determine intersection point. So we should know that what is the formula to determine intersection point. So if I want to determine intersection point, we have two types of clipping here. We have vertical clipping and next we have horizontal clipping. Then we will get two different formulas here. We will get vertical intersection points as well as horizontal intersection points. So before calculating or before discussing what is the intersection formula, I would like to give one example here. What is the meaning of vertical clipping, or what is the meaning of vertical intersection point? So assume that one clipping window is given. Its size is x minimum y minimum to x maximum y maximum. This is the range of the clipping window. And against this clipping window, I drawn one line segment P1 to P2, where P1 is x1 comma y1. This is the first end point of the line segment. Where P2 is x2 comma y2. This is second end point of the line segment. So now we need to perform vertical clipping on this line segment. So if you want to perform vertical clipping on this line segment, you will get two intersection point. First, I'm reading from bottom to top. First intersection point you will get where line segment it touches or it crosses the boundary of the clipping window or bottom edge of the clipping window. When line segment crosses bottom edge of the clipping window, I'll get one intersection point here. Means I need to calculate this is a one intersection point here. I will get one more intersection point where line crosses top edge of the clipping window. When line segment it touches or it crosses top edge of the clipping window, then I will get one more intersection point here. Means here I need to determine vertical intersection point with respect to this example, because I drawn line vertically with respect to clipping window. Then I need vertical intersection points. So how to get vertical intersection point means we are using following example here. We are using following formulas. So here I written case 1 and case 2 with respect to vertical clipping. When line crosses bottom edge of the clipping window, I will tell it is case 1. When line crosses top edge of the clipping window, I will tell case 2. Whenever you are solving problem, if you want to calculate vertical intersection point where line crosses bottom edge of the polygon, bottom edge of the clipping window, you need to calculate bottom intersection point using the formula x equal to x1 plus y minimum minus y1 into 1 by m, where m is slope. So the simplified formula for this is x equal to x1 plus y minimum minus y1 into x2 minus x1 divided by y2 minus y1. Means here I need to calculate what is the new coordinate position of the bottom intersection point only with respect to x-axis, but there is no any change with respect to y value. So y value is equal to y minimum. Y value is equal to y minimum. So this is how to calculate bottom intersection point. So this is nothing but our x and y coordinate value. X and y represent new intersection point. So with the help of intersection point to a endpoint that lies inside the clipping window, we need to accept that endpoint of the line segments and we need to display that part of the line segment on the screen of the monitor. This is case 1. When line segment crosses top edge of the clipping window, then we'll get case 2. So whenever you are solving with respect to case 2, formula is x equal to x1 plus y max minus y1 into 1 by m, and you need to simplify this formula. I didn't simplify it. You simplify this formula like how I simplified here, and y value is equal to y max. There is no any change with respect to y axis, right? Y is equal to y maximum, but only x coordinate value we need to calculate using appropriate formula. So this is vertical clipping. Similarly, we have horizontal clipping also. So when line is drawn vertically against the clipping window, we will get vertical clipping. When you draw the line segment horizontally with respect to clipping window, you will get horizontal clipping. Again, we have two cases. Case 1 where a line crosses left edge of the clipping window, then we will get case 1. Case 1 formula is x equal to x minimum, y equal to y1 plus x minimum minus x1 into m. If line crosses right edge of the clipping window, then we will get intersection point here, second intersection point. Then formula is x equal to x max y equal to y1 plus x max minus x1 into m. So these are the vertical intersection point calculation formula and horizontal intersection point calculation formulas. So these are the four formulas you need to remember whenever you are determining intersection points. So I'll move to case 4. I'll move to case 4. Assume that assume that case 1 is also false, case 2 is also false, case 3 is also false. Assume that case 4. So what is the case 4 means? After calculating output 1 and output 2, assume that one of the output is not equal to 0 and another output is equal to 0. For example, if O1 is not equal to 0, if O1 is not equal to 0 means P1 endpoint lies outside the clipping window and O2 is equal to 0. It means that second endpoint P2 lies inside the clipping window. If one endpoint is inside the clipping window and one more endpoint is outside the clipping window, then we need to determine only one intersection point with respect to the endpoint that lies outside the clipping window by using previous intersection point formulas. So in the case for one endpoint lies inside the clipping window and one more endpoint lies outside the clipping window, and we need to calculate intersection point recursively with respect to case 4. So as you can see this example, which line indicate means with respect to case 4, I can say that P5 to P6. I can say that P5 to P6. So P5 is lies outside the clipping window, P6 lies inside the clipping window. So in this case, I need to determine only one intersection points. So I explained how to calculate intersection points also. So we have 4 cases. So you can see the advantages of Cohen-Sutherland line clipping algorithms. So as I said already, Cohen-Sutherland line clipping algorithm, it is one of the fastest line clipping algorithm among the various types of line clipping algorithms. So as you can see that I listed, it works fine when there are many line segments are there. This is the first advantage. Second advantage is this Cohen-Sutherland line clipping algorithm can be extended to clip the three-dimensional object. As I said, it is a faster. Fourth one, it reduces wastage of execution time when point lies outside of the clipping window. So these are the 4 advantages of Cohen-Sutherland line clipping algorithm. But we have only one disadvantage, that is Cohen-Sutherland line clipping algorithm, it uses recursion concept. This is the disadvantage of Cohen-Sutherland line clipping algorithm. So today I would like to conclude here only. I want to stop here only. So just I would like to revise what are the concepts today we discussed. Today we discussed what is clipping, what are the clipping algorithms we have in computer graphics, and we also discussed how to clip a point and how to clip a line using Cohen-Sutherland line clipping algorithm. So Cohen-Sutherland line clipping algorithm working principle is very simple. First we need to divide entire weaving plane into 9 regions and we need to assign unique outcode to each region of the weaving plane. Next we need to enter two endpoint of the line segment, that is P1 and P2. Next we need to calculate what is the region code or what is the outcode of the each endpoint of the line segment. After calculating outcode of the each endpoint of the line segment, then we will get 4 cases. We need to check whether outcode 1 and outcode 2 is equal to 0 or not. If both the outcode values are is equal to 0, it means both the endpoints are lies inside the clipping window we need to accept that particular line segment. Second case is if outcode of the both the endpoints are not equal to 0, then we need to perform bitwise AND operation between outcode 1 and outcode 2. So after performing bitwise AND operation between outcode 1 and outcode 2, if the result is not equal to 0, if result is not equal to 0, it means that both the endpoints of the line segment lies outside the clipping window. We need to reject complete line segment. No need to display that line segment on the screen of the monitor. Case 3 is after performing bitwise AND operation between outcode 1 and outcode 2, if result is equal to 0. If result is equal to 0, it means that part of the line segment lies inside the clipping window, but both the endpoints are lies outside the clipping window. Then we need to determine two intersection points with respect to this case. So we will get two types of intersections. One is called vertical intersection called vertical clipping and horizontal intersection called horizontal clipping. So by using appropriate intersection point calculation formula, we need to calculate either one intersection or two intersection point. So in the case 4, we discussed one of the endpoint lies inside the clipping window and one more endpoint lies outside the clipping window. So in this case, we need to determine only one intersection point using intersection point calculation formula. And whichever the part of the object that lies inside the clipping window, from that intersection point to the point that lies inside the clipping window, we need to display only that part of the object on the screen of the monitor. So this is working principle of Cohen-Sutherland line clipping algorithm. Thank you.